Hi guys, and welcome to another CHIP technical tutorial. In this edition we're going to talk about real-time clocks. So the idea here is that when the chip boots up, it doesn't actually know what time it is. It doesn't know the real-time clock, and that's because the chip doesn't have battery backup in it. Now when the chip boots and you bring up a clock or a calendar, you probably do see that the chip knows what time it is. And the way it's done that is that if the chip is network connected, then the chip will contact the internet, find some some time servers, and download the current real-time clock over the internet. And from then on, it just remembers it until the next reboot, in which it repeats. However, if we're running CHIP without internet connectivity, for example headless in some project in some dark shed somewhere, then if you want to know the real time, you may not have network connectivity. So we need to have some mechanism whereby the chip can remember its time between boots. Now one solution to this are the super cheap real-time clock modules. Now you can find these on eBay for well under $1, and what these are I2C CHI2C devices which have battery backup capabilities on them. So we tell this device at some point in time what time it is, and then for the next year or 2 years or until the battery runs out, this module will keep remembering the time. And then when your chip boots, your chip can be configured to ask this device for the time, and chip will know what time it is. So let's go have a look at this. Let's see what we have to do to get this running. So I'm going to assume you've got yourself one of the modules. You've got one of the real-time clock modules. The next thing we're going to want to do is we're going to want to wire up a circuit. Now this is a schematic. It looks horribly complicated, but I'm going to leave that on the screen for a few moments. This is the right-hand side header of our chip, and from this we need the 5 volts and the 3 volts and the I2C bus, and of course ground. The reason we need 5 volts is that the real-time clock module is a 5-volt device. Now because it's a 5-volt device, that means we cannot wire data coming in from the real-time clock through the I2C data bus. We cannot wire that directly into the headers of chip. Otherwise we will damage our chip. So I've got here a level shifter component where the SDA signal comes in the high voltage, the low voltage 3.3 is now mapped to SDA, and vice versa. So this is what the schematic looks like on a breadboard circuit that I wired up. This is what it looked like in physicality. Again, lots of wires floating around the place, but that's just following my schematic. I'm not the neatest wirer of all time. One could have done links on a breadboard. It would have been so much nicer. But here we see the real-time clock module. Here we see my chip, and it's wired into I2C. Alright, so enough of the talk. Now let's go have a look at it from a software perspective. Let's see what it looks like from the terminal. So here I am. I'm logged into my chip. For this, I'm going to switch over to be a root user. So sudo bash, I become root. I2C detect -Y2, and what we're looking at here is I2C bus number 2, and we see that we have a new device on the bus at address 68 hex, and 68 hex, that is our RTC, our real-time clock device. So at this point it can be seen on the I2C bus, but the kernel driver for the real-time clock, although it's loaded, it has not been exposed as a device. So if I go to /dev and look for anything that begins RTC for real-time clock, we got nothing. So the solution to this is we go to our sys file system, our class, our I2C adapter, our I2C2 directory, and in here we have various bits and pieces relating to the I2C bus number 2. Now, if we echo the magic incantation DS1307, which is the name of the real-time clock module, and we say it's going to be present on I2C address bus address number 68, and we echo that into new device, and it silently does its thing. If we now go up to /dev, and we run the command ls-l rtc, ta-da! We see it. We see we have some new entries here for the real-time clock. Wonderful, wonderful. Now we're ready to use the hardware clock. So there's a command called hardware clock, and the first thing we want to do is synchronize the value on the hardware clock to our current system time. So if I ask the machine what time it is, it says it's August the 6th, about 1:10 in the afternoon. If I now run the command sudo hardware clock -- system to hardware clock, give me some debug, don't adjust my system time, and save everything in universal time, run this command, and it now tells me that it has now synced up the current time on my chip to the hardware time on the clock. So I pushed the current time on chip to the current time on the hardware clock. Now, finally, if I run sudo hw clock -- show, what it's doing is it's polling or interrogating the hardware clock, the real-time clock, and this is the time that is now on the hardware clock. Okay, now all this sounded like gobbledygook, but if I was to reboot my chip and it was not connected to the internet, the chip would have no idea what time it is. But if I now, let's look at bring up the help menu for hardware clock. If I now were to run hw clock --HC hardware clock to system, it sets the current system time to the value stored in the system clock. And that's it. That's really all there is to say about this. The idea being that we can have a partner module to the chip which maintains a real-time clock which is battery backed up and will last for years. When chip boots, chip can be configured to synchronize its system clock, i.e. that's the time that chip itself believes it is, to the value which is ticking along merrily in the hardware clock. And all of that for under $1. I hope you found this useful. I look forward to making lots more chip technical tutorials in the future. Bye for now.